Welcome to day 5, continuity. We're going to determine if a function is continuous or not continuous. It's very obvious to tell from a graph if it's continuous or not. If you look at our two examples over here, a graph is continuous if it has no breaks in it, like the one on the left, and if it's discontinuous, if you see it has a break anywhere. Okay, in other words, to draw the graph on the right, I would have to lift up my pencil at some point to draw that graph. On the one on the left, I could draw it without having to take my pencil off the paper. Okay, same thing over on the next one. The one over here on the left is continuous, and the one on the right is not. Okay, so there's a couple of types of discontinuity. One type is called removable discontinuity. It's just a basic hole in the graph, something that looks like this. In other words, if I put a dot in that spot, the graph would not be continuous. Okay, that's why it's removable. I could do something simple by putting a dot on a graph. Non-removable are two types, and that's when we have a vertical asymptote or some sort of jump or gap in the graph. So if we had a vertical asymptote and I had a graph that looked like this, obviously there's a break in the graph at the vertical asymptote. A jump or a gap would be something like you see above in both the discontinuity ones, where you have a graph that goes like this and like this. There's a gap or a jump, and obviously this other one has a VA. That's non-removable. I can never do anything simple to make it continuous. Let's identify these graphs as either continuous or discontinuous, and if it is it removable, non-removable? Well, this has no breaks in it. This is continuous. This does have a break in it, so it is discontinuous at x equals 1, and it is non-removable because there is a jump or a gap. I'll call it jump. This next one, I see a lot. It is discontinuous at many spots. So this graph has 4 different spots of discontinuity. First, it has it here at -2. There is a jump there, so it's non-removable. You can see that gap at x equals 0 right here in the middle. There is a VA there, so that's also non-removable. At x equals 2, it's just a hole in the graph that is removable. And at x equals 4, there's a small little gap or jump between those two different parts of the graph. This next graph is discontinuous at x equals whatever the c value is, because there's a VA, so it is non-removable because of a VA. And these last two, even though this one is a piecewise function, it is continuous. And this last one is also continuous. So now we're going to go into the true definition of something being continuous by using our algebra rules, what we've done so far this year with limits and values. A function is said to be continuous at some value x equals c, where c is any real number, if and only if the limit as x approaches c of the function is equal to f of c. This basically says the limit of the function at x equals c, which has to equal some number, is equal to the value of f of x at x equals c, which is just some number. C is just some number. Okay, we looked at these graphs already. We've talked about limits and values. A value is always looking for a solid dot, and a limit doesn't care. What we're saying now is that the limit at that value of x equals c is also equal to the value of f of c. So what we need is three things to happen, and all three have to be true. First, the limit has the value has to exist. So in other words, f of c has to equal some number. Let's call that number a. The second part that has to happen is that the limit exists. For the limit to exist, so we're saying the limit as x approaches c of f of x has to equal some number. Let's call that number b. For a limit to exist, we've talked about this before in graph, the left side has to equal the right side. It's the only way a limit exists. So we're saying the limit as x approaches c from the left of my function has to equal the limit as x approaches c from the right of that same function. Okay? And we've done this many times on graphs where the left side has to equal the right side. That makes the limit exist. And then finally, what we're trying to show is number 3 is that part 1 has to equal part 2, or from where we said part 1 we said that that value would be a and part 2 was b. A has to equal b. Okay, this is what we're trying to show. If any part of these is false, so if all three parts work, it is called continuous. If this works for every point on the domain, it's called continuous on the whole function. Conversely, we have a function is not continuous if any part 1, 2, or 3, we have 3 parts, 1, 2, and 3. Part 1, the value exists, part 2, the limit exists, and part 3, part 1 equals part 2. If any part is false, then it is not continuous. Let's go through some examples. Okay, I drew graphs for the 3 examples. We're going to do part A is where part 1 is false. Part 1 is the value question. F of 2 is undefined. There's no solid dot there. So once I know it's undefined, I know it's not continuous any longer. But part 2 is true. The limit as x approaches 2 from both sides of the graph is equal to 4, because you can tell that the left side of the limit is equal to the right side limit. They both equal 4. They both meet together. This is the left side limit, and this is the right side limit. They both meet at y equals 4. Okay, the next one, let's see if it's true. Well, let's see, the value is true at x equals 2. I do have a solid dot, so f of 2 is equal to 4. But the limit as x approaches 2 of this function is dne, so part 2 is false, and you could see that the left side limit as x approaches 2 from the left of the function is equal to, well, it's right here. It is right here. That side is equal to 4. And the limit as x approaches 2 from the right side of this function, the right side limit is this side is the right side. It stops at 2. That side is equal to 2. And since these guys do not equal each other, that's why the limit in general is dne. And the last one deals with the idea that part 1 and part 2 are both true. Well, part 1 is the value, so f of 2, I have a solid dot at 2, so that's true. Part 2, I had the limit as x approaches 2 of this function is equal to 4, because you can see that the left side and the right side do meet together at y equals 4. So I could write that down as the limit as x approaches 2 from the left of the function is equal to the limit as x approaches 2 from the right of this function. They both equal 4. So right now I have part 1 and part 2 are both true. They both have values. The value exists, the limit exists, but this is not a continuous function because, as you can see right now, part 1 does not equal part 2. Therefore, it is discontinuous. These next two examples deal with piecewise functions, and we're going to see are they continuous or not continuous. Both of them have two pieces, and you could draw them, but I'm actually going to show you an example where you don't even have to draw a piecewise function. But first, I'm going to draw this piecewise function. The left piece is a parabola with vertex 0, -2, and I drew that there. The a value for this is equal to 1, so it's be concave up. So I went over 1 square. 1 squared is 1 times 1 is 1. It says including 1, so I made it a solid dot. It's a buddy point. I went from the vertex. I went over 2 squares. 2 squared is 4. I went up 4. I went back to the vertex. I went over 3 squares. 3 squared is 9. And I went up 9. And I could draw this parabola like that. And there's your left piece. The right piece is just a linear equation. I'm going to start with x equals 1 because it says start at 1. I plug 1 in there, get 2, but it's not including 1, so it's an open dot at 1, 2. And I could just either do a slope of 4 from there or plug in the next number 2. I get 2, 6. And now you can just get a nice line, and that's a terrible line. So I'm going to erase it and try it again. And there we go. And that's the right piece. And now I have my graph drawn. And I could do my 3 steps. You always have to do 3 steps. Step 1. I'm using x equals 1. Does f of 1 exist? Well, f of 1 is looking for a solid dot, and it does. It is equal to -1. Step 2. Does the limit as x approach 1 exist? Well, let's see. Does my left side in red meet my right side in green? The answer is no. That is DNE. So even out of notation, my left side in red, the limit was from the left side of 1 was equal to -1. The limit from 1 from the right side is equal to 2. They don't equal each other. So right now for part 3, part 1 obviously does not equal part 2 because 1 is -1, 1 is DNE, so this is discontinuous. This is what the graph is. And it's all for the first one. So number 2 is again 2 pieces, a left and a right piece at x equals 0. My left piece is a line. I plugged in 0, I got 0, 1, but it's not including 0, so it's an open dot at 0, 1. And I can plug in any numbers left of 0. I plugged in -1. And I can get all of these. This is what the graph looks like on the left side. Nice little line. The right side is parabola, vertex 0, 1, but it's going to be a solid dot, so I'm going to fill in this open dot I had before. And then I can do another point after that, or I could use my a value is equal to 1, and I could go over here. I could start at my vertex and go over 1 square, and go 1 squared is 1, 1, 2, go back to my vertex, go over 2 squares, 2 squared is 4, go up 4 here, go back to my vertex, go over 3, 3 squared is 9, and go up 9. And I get this half a parabola over here, and this is my right piece. Now let's see if I can follow my 3 steps. Step 1. Does f of 0, because I'm using x equals 0, does it exist? Do I have a solid dot there? I do have a solid dot at 1. Part 2. Does the limit as x approaches 0, not from the left or right, from both sides, does it exist? And the answer is Yes, it does. The green and the red meet together at y equals 1. So I can do the limit as x approaches 0 from the left of this function in red is equal to 1. And the limit as x approaches 0 from the right of this function is equal to 1. So I have shown that my left side is equal to my right side. That's why I get 1. And then finally, step 3, part 1 does equal part 2. Therefore, this graph I just drew is continuous. Ooh, be nice if I wrote it nice and neat. Continuous. Now for number 3, I'm not even going to draw a graph. I don't have to. I could still figure out my limits on the left side and the right side and this and that without a graph. This one has 3 pieces. It's got, I'm going to break them up into 3 pieces. It's got a left piece for x being less than 1. It has a right piece when x is greater than 1. And it has a center piece when x is equal to 1. So part 1 is right here. F of 0 means when x equals 1, I'm using that center part of the graph, and f of 0 is equal to negative 1 according to the center part. This little negative sign says from the left part. So I have to use the left part, and I'm going to plug 0 in here. So I'm going to do f of 0 from the left is equal to negative of 0 squared. Well, that is just equal to 0. Now let me do it from the right. Well, because that plus sign means from the right side, so now I'm going to do f of 0 from the right piece, and that's going to be the square root of 0. That is also equal to 0. So my left side is equal to 0, my right side is equal to 0. So in general, this is from both sides, and since the left is equal to the right, my limit as x approaches 0 of the function is equal to 0, because I have shown from part B and part C that the left is equal to the right. And then finally, my 3 steps. Step 1, f of 0 is equal to negative 1. That's the value part. Step 2, the limit as x approaches 0 of the function, which was part D, and we got an answer of 0. But as you can see, part 1 and part 2 do not equal each other. So part 3 says part 1 does not equal part 2, so this is discontinuous. And for this last part, I'm trying to find the values of a and b. I have a and b inside these functions here that will make this function continuous at x equals 1. So I have to do my parts. Part 1 says f of 1. Well, I have 3 parts again here. I have a left, a center, and a right, and f of 1 is using the center part, and that value is equal to 5. Step 2, I need the limit to exist, or better yet, I need the left side equal to the right side. But not only does the left side have to equal the right side, for this to be continuous, I also need this to equal part 1. So when I do the left side, I'm going to plug, well, that's bad. I'm going to plug in x equal 1 in both the left and right side and make them both equal to what I got from part 1, and that was 5. So for the left side, I got, plugging in 1, I get 3a 1 minus b, and that gives me 3a plus b is equal to 5, because I have to have it equal to 5. When I do it on the right side, I plug in 1, I get 2a square root of 1 plus b, and that gives me 2a plus b is also equal to 5. Oh, my bad. Made a mistake. This is minus, I don't know why I said plus b, this is minus b. 3a minus b is equal to 5, and now I have a very good system here, very convenient system here. I have two equations, two variables a and b, or two parameters a and b, and right now if I add them together, the b's cancel out and I get 5a is equal to 10, so a is equal to 2. I could go ahead and plug that in either one of them. I'm going to plug it in here. 2 times 2 plus b is equal to 5. 4 plus b is equal to 5. be is equal to 1. So if I wanted to rewrite these equations on top here, I could rewrite these functions as plugging in, this would be 6x minus 1, and this one would be 2 square root of x plus 1, and that would be the formulas to make this a continuous function at x equals 1.